discussions and interactions. So our next speaker is Kunal Talwar from Google, and he's going to talk about differential privacy.
Thanks, Dan. Thanks to the organizers for inviting me. It's always great to be here. So I guess my goal today is to just give kind of a high-level introduction to what differential privacy is, tell you a little bit about how you can actually achieve it. So stop me anytime if you have any questions. Yeah. OK, so let me start with this map. How many of you have seen this map? No. OK. I guess you get very different reactions from different crowds. OK, so this is a map of London in 1854, when there was a big cholera epidemic called the Broad Street epidemic. 600 people died in a week. Almost the whole neighborhood evacuated, and nobody knew what was causing it. At the time, people didn't know what caused cholera. And this gentleman, John Snow, went there and he drew this map. So so this is the map he drew, where each of the black dots is one case of cholera. Right? And he stared at this map and basically from this map concluded that cholera is waterborne, and it was this pump right here that was causing it. So if you look at all the black dots, basically all the black dots lie in the Voronoi cell of that particular pump, what you would now call a Voronoi cell of that particular pump. All these houses were getting their water from that pump that was infested with cholera. And this actually founded the field of epidemiology. So I think this was one of the first illustrations of the use of private data for public good. And I guess, as we all know, there's a lot more data now, and we can hope to use a lot more of it for more public good. And this is probably what was on William Well's mind back in '97, when, as the governor of Massachusetts, he decided that all the medical records of the state employees, so the state of Massachusetts is the insurer for all state employees, so it has access to all their medical records. He decided this is a large amount of useful data. Mining it could actually be very useful, so he decided, let's make it public. Of course, this is private data, so you can't just publish everyone's medical records. So he did what was kind of at the best possible anonymization at the time. So people, all personally identifiable information was stripped off, and the data was released. It was about a week before he got a letter in his mail with his own medical records. And Latanya Sweeney was the person responsible for that. She was then a graduate student at MIT. And here's what she did. She went to the city of Cambridge, paid them $20 to get the voter rolls. The voter rolls have a fair bit of information like this: name, address, party affiliation, zip code, date of birth, gender. And some of these fields were also present in the medical data set. It's reasonable to say that the zip code is not a personally identifiable information. Tons of people live in my zip code. Same for the date of birth and gender. But what she realized when she did a join on these two data sets was that the intersection is actually very highly personally identifying. In this data set, basically if you run the join on these two data sets, most people here become unique, including William Weld. So this is, I think, an instance of kind of the risks of using private data for public good, which is that making such high-dimensional data private is a very difficult task. We don't necessarily know what kind of information can be identifying when coupled with other auxiliary data sets. In this case, a very simple auxiliary data set, the voter list, is enough to uniquely identify William Weld and everyone else in the database. But it's not just limited to these three attributes. These are now routinely removed and considered PII, personally identifiable information, when you release medical data. But there's other ways. So further work that Latanya has been doing, for example, shows that knowing a little bit about the visit date and the diagnose that you could get, say, for example, from a newspaper article about somebody who had an accident. They probably went to the nearby hospital on this date. So you have one tuple of visit date and prognosis for this person. And from that, you can actually get a lot more information. You can get their whole medical record. So I guess this is the tension that differential privacy is meant to address. There's private data, releasing it carries a lot of risk. I'll give you a few more examples of this kind of privacy attacks. Then I'll give you a formal privacy definition that tries to protect against these kinds of, and these and other kinds of attacks. And then I'll give you a little bit, little flavor of how you can actually go about designing differentially private algorithms. Good. Let me just, so just to reiterate, we saw two examples of data sets that contain sensitive information about individuals, but there's a lot more. They are everywhere. Governments have them. Businesses have them. And as we saw, analyzing these data sets can be very valuable. We do want to learn that it was the Broad Street pump that was causing cholera. We want to be able to learn from analyzing data sets that smoking causes cancers. But at the same time, we don't necessarily want to learn from the data set or from the analysis whether I smoke or not. And there are many good reasons to guarantee privacy. I won't get into that. But let me tell you about a few more stories that illustrates other aspects of this, of the privacy risks. How many of you have heard of the Netflix prize? This should be easy. Good. Okay, so Netflix prize, for those you haven't heard, was this competition that I guess one of the first big popular kind of crowdsourcing data analysis competitions, where they basically released a large data set containing, I think, a couple of 100 million movie ratings of 500,000 people. And the task was to kind of use this large data set to be able to predict how certain individual will, how much this individual will like a movie that wasn't actually like another candidate movie, right? So they released this data set. Movie rental records are actually sensitive, not just from the business point of view, but also actually legally protected. And so they did actually remove all personally identifiable information. In this case, what they released was something very simple. Basically, it was a large matrix where the rows were people, the columns were movies, and the populated entries was what was the rating of this person for this movie. Of course, the persons were all just replaced by random numbers. The movies were movies. I guess movies don't need to have privacy. And I guess it was 2 weeks in this case before Narayanan and Shmatikov published a paper showing that you could actually identify people in this matrix if you know a little bit about them. So if I know, for example, 3 movies that you watched, along with the dates you watched them on, or the week that you watched them on, which, for example, you could have told me about a movie you watched if you were my friend, that's enough to completely identify a person in this database and learn about other movies that they watched and may not have told you about. And I guess what this example illustrates is something more worrying. So in the case of medical records, the auxiliary information that allowed the identification was stuff like zip code and gender, which it's reasonable to say that your zip code probably is not important data about. If I wanted to learn whether smoking causes cancer, don't need to learn your zip code to be able to do that. So one could hope to share data sets with these fields retracted and get some utility out of it. In this case, all that was published was this matrix. If you want to share this matrix, there's no retraction here that could have prevented this kind of attack and still allowed any reasonable inference.
Were the movies labeled?
Yeah, the movies were labeled.
Netflix could have permuted them randomly. And
okay, good point. So they could have done that, but that would severely restrict utility. So in this case, what was also useful to actually build the recommendation system and was true in all the winning entries, any entry that made it to the top of the list, had the property that they used not just the matrix, but also used the fact that this is a John Wayne movie. If you like one John Wayne movie, you probably like the other ones as well. So attributes of the movies itself were useful information to build the recommendation system. So I guess the moral from this is there is auxiliary information in this world, things that you don't publish but people may have access to. It may come from the voter rolls. It may come from what you tell me about what you watched. It may even come from IMDb. So in fact, in their attack, they showed that you could identify IMDb users from what they rated on IMDb. And kind of guarding against auxiliary information is very difficult. It's if you want to think about dataset release as an isolated problem, it makes it easier, but it doesn't actually solve the problem because there are auxiliary datasets that do exist. Here's one last story. So this is this paper that's now known as Homer et al. I don't expect you to read the title. What this paper basically showed was okay. So do we know what a GWAS study is? Genome-wide association study. So genome-wide association studies are these studies where you try to figure out how your genotype, how your genes affect your likelihood of getting a certain disease. Right? And the way you do such a study is, to simplify a bit, you collect a large population of people who don't have a disease, a large population of people who do have a disease. You sequence these guys' genome, you sequence these guys' genome, and then you look for correlations between certain what are called SNPs and the disease. Okay. And if you see a large correlation, that probably suggests that this gene has something to do with the disease, and then you can investigate further. So these have become, I guess, very frequent in the last decade or so. And for a while, NIH required you to actually share a fair amount of raw data when you ran such a study. So if NIH funded your study, you were required to publish, say, all one-way marginals, all correlations, not just the ones that you found to be significant, but actually all of them. And what this paper showed was that if you do that, if I have access to all these one-way marginals, and if I know your DNA, say from the glass that you just used to drink water from, I could actually figure out whether you are in the control group or the disease group. So even though all that's being published is these very, very aggregate information, over thousands of people, we are averaging the frequency of a certain SNP. The fact that I have actually millions of these one-way marginals, even with some noise added, is sufficient to actually identify people in this database. And I guess this is what happened as soon. So basically, even before this paper was published, NIH actually flipped its requirements and prohibited people from sharing these one-way marginals. So I guess what this example illustrates is that even very large-scale aggregate data, which looks completely innocuous, can be actually very revealing. And I guess I didn't get into more examples, but there are examples where even when you don't actually publish anything, you just act based on some database, even that can be sometimes revealing. In all of these cases, I think one thing that's worth noting is that the experts who were publishing the data had all the incentive to worry about privacy. And yet, even the best known techniques at the time were not enough to actually give any privacy guarantee. And in some sense, the reason for that is, I would argue that all these approaches were somewhat ad hoc. You come up with a way to how you could attack the system, and then you put one band-aid to try to fix it, and you repeat. But because our imagination is limited, it's very hard to actually use this approach to really guard against all possible attacks. So I guess differential privacy is one approach to solving this problem. So let me define that next. Okay. So I guess one kind of insight that came from, I would say, cryptography is that privacy is not a property of what you publish. It's a property of the mechanism you use to publish. In the same way that in cryptography, it's not the ciphertext that's secure, it's the fact that the ciphertext is generated using some mechanism that makes it secure. So privacy will be a property of the mechanism that's used to generate the data. So it will be convenient to think of of an interactive setting, though we don't really need that requirement, and we'll kind of use this to publish things later. But imagine you have an analyst that's trying to learn something about the database. So here's the database, and there's a curator sitting in between that takes questions from the analyst and gives responses. So you can ask it how many people in this database smoked and got cancer, how many people did not smoke and got cancer, and so on. And based on all those answers, you can build your model, you can learn stuff. What the curator will do is, so the curator is kind of a wall between the analyst and the database. It will get the real answers and potentially adds, and in fact, in most cases, add some noise to the answers before returning them. So to define differential privacy, it's convenient to think of two universes. So there's the blue universe, where I'm in the database. There's one row in the database that contains all of my data. And there's the red universe, where I've gone in and completely erased my data from the database. So here I exist, I'm in the database. Here I don't exist, I'm not in the database. What differential privacy would intuitively say is that the analyst that's interacting with the curator, it can't tell whether it's in the blue universe or the red universe. Based on the interactions, the analyst is not able to figure out whether I'm actually even in the database or not. These two words look identical to the analyst. And I guess it's reasonable to say that in this universe, in the red universe, when I'm not even in the database, well, in this universe, the database doesn't even know I exist. It can't possibly leak anything about me. The blue universe looks almost the same as this one. This is why it's a privacy definition. Yeah?
All right, so in the red universe, I can infer lots of probable characteristics of you still.
Great question. So if, for example, you know me personally and you know that I smoke, before the analysis happened, you didn't know that smoking has anything to do with cancer. After the analysis, you learn that smoking causes cancer. And therefore, you can infer that I am now likely to get cancer. That is an attribute of me. Guess what I would argue is that the secret that smoking causes cancer is not my secret to keep.
What is the agency to participate in the database or not?
So you could distinguish between secrets that I have, which are my secrets, and there are things which are my secrets, but other people have them. Other people know them. I have no control in whether or not those get released or not. What differential privacy guarantees is that things about me that I have will not be revealed.
Well,
And-
something like your income level, if I get access to experience database or aggregate statistics from the IRS,
Mhm.
right? So that's something which is, I don't know how to. I'm
So I think there may be valid situations where you may not actually even want to do a certain study. But whether or not we want to do a study that tells us whether smoking causes cancer is a societal decision. I have no control on whether that study happens or not. What I can control is whether I participate in the study or not. This definition says that by participating in the study, I do not change the likelihood of any event. And this actually is a very crucial distinction. If you want a guarantee that the adversary cannot learn anything about me whatsoever, there's actually a theorem that says that you cannot actually give any information whatsoever. So what differential privacy is an attempt to kind of tease apart this distinction between, I guess, what Frank calls secrets that I have versus secrets about me.
I see.
If I don't own that secret, I have no agency to protect it. Differential privacy will not necessarily protect it.
So later on in the talk, are you going to reconnect then that distinction to some of the privacy questions, around data analytics?
My talk is going to do some of that.
Okay, great. Thank you.
Okay, so, so I guess there's a lot of discussion on this question. There's a very nice blog post by Frank McSherry that I would recommend you read that basically addresses exactly this question. But any more questions? Yeah.
Does it make sense to remove more than one person, or can you use induction a few times?
Yes. So I guess I'll get to that. Yeah. Okay, so let me tell you formally what the definition is. As I said, it basically says that the distribution, so this curator will be a randomized algorithm. This definition says that the distribution in the blue universe is almost the same as the distribution in the red universe. Formally, there's a parameter called epsilon. So epsilon differential privacy says that this likelihood of this event happening, of any event happening in the blue universe, is within e to the epsilon of the same event happening in the red universe, and vice versa. So for any two databases that differ in one individual by addition or deletion, any event is almost as likely in the blue universe as it is in the red. So this parameter epsilon measures how much privacy is being leaked. We'll think of it as a privacy loss. We'll normally think of it as a small constant. So e to the epsilon is like 1 plus epsilon. We'll also look at a relaxation of this definition called Epsilon-delta differential privacy, where you allow a small probability of kind of failure. So you should think of delta as being very, very small, as small as the probability of your password being leaked. So this is kind of at least polynomially small or even smaller, epsilon is a small constant. Right, so I guess this delta doesn't really change, at least my intuitive understanding of the definition, by much, but technically it turns out to be very useful to have a very small slack. Yeah.
So but without the delta, it's like a Kale divergence. And
Yes.
with the delta, it's like a total variation, almost.
No, it's not quite as weak as total variation. So I guess, so without the delta, it's a max divergence guarantee. So Kale divergence kind of measures the expectation of the dog. This is the L infinity version of Kale divergence. With the delta, it's sort of like a delta slacked version of L infinity. Okay, so here are two nice properties of this definition. First, you can take an output of a differentially private mechanism, and then you can do whatever you want with it. You can add 1 to it, you can run a join with your favorite voter list, you can do whatever, it stays differentially private. To give the definition, I didn't have to utter the words auxiliary information. This definition by itself says no matter what auxiliary information you have, if you do anything with output of a differentially private mechanism, any post-processing preserves differential privacy. The second important property is composability. So if you run one differentially private mechanism and then you run another differentially private mechanism, the sum total of the two, the total interaction, is still differentially private. The privacy parameter epsilon kind of degrades gracefully. So what this allows us to do is to sort of use small differentially private building blocks and put them together and reason about the union of these building blocks.
Can't you adversely use it to somehow get and multiply the epsilons?
Yes, so if you keep running an arbitrarily large number of differentially private algorithms, then your epsilon will go to infinity and you won't have any privacy. So epsilon is kind of your, it's kind of the currency. You can think of it as, since we are in Berkeley, if you spend a small amount of money on something, it seems small, but if you keep doing it over and over and over again, it can become large, right?
No, but one could imagine that there is a mechanism so that somehow, after every query, kind of really randomize the things, so the epsilon don't necessarily accumulate.
So that would be nice, but unfortunately, at least in many settings, we know that they do accumulate in the sense that if you answer a lot of questions about the same database, either the answers become very, very inaccurate over time, or you essentially leak the whole database. So there are privacy attacks showing that even ignoring differential privacy, if you want any notion of privacy, you do need to either control the number of questions you answer or the accuracy with which you answer them. Yeah.
Have people thought about limiting F to be in P or P space or something, and maybe getting more from that?
Yes, so there's some work in those lines in the single party setting. We don't have any evidence that it helps. There are settings where it does help. So if I have a database and you have a database and we want to jointly compute some function, then assuming some computational restriction on the adversary does allow us to help a lot. Yeah.
Oh, and how about delta? Does it compose like
Delta composes as well, yeah. Good. So actually, I'll say more about composability later in the talk. It's actually a lot better than this when you compose multiple times. But One more thing to add to answer to your previous question. The other property that I didn't write down here is that the way the definition is written, it's easy to see that if you remove 3 people from the database, then you have sort of 3 epsilon differential privacy. So small groups of people can be removed from the database. They still have, so families still has privacy. The community will not have privacy because we want to learn something about the community. Good. So I guess this is a slide which essentially was to have the discussion that we sort of already had. Differential privacy does not say that your beliefs about the world do not change. If you came from Mars and thought that humans were octopuses and had 8 feet, after interacting with the database, you will learn that I only have 2 feet. Right? But that deduction would happen even if I was not in the database. And in some sense, that is not my secret to keep. And I guess epsilon actually accumulates over time. It limits how much you can, how many queries you can answer. Good. So let me actually quickly give you one example of how you can get differential privacy. So imagine you are trying to answer a simple query such as a count query. You are asking how many people in the database smoke. So this is some overall people of some predicate, some 0, 1 predicate. The private approximation to that, this is basically you output the function plus noise drawn from this Laplace distribution, which is basically this distribution here. It's an exponential distribution symmetrized. Why does this give differential privacy? Well, if you look at the blue universe versus the red universe, the correct answer can differ by at most 1. So I'm drawing in one case from this distribution. In the other case, I'm drawing from the same distribution shifted by at most 1. The way this function is defined, it's easy to see that the property, it has a property that the ratio of the density at any point is at most epsilon, where epsilon, I guess, depends on this lambda here. Yeah.
So, now if I use pseudo-randomness to generate Laplace, does that mean that I better have a polynomial time adversary?
Yes, or yours, yeah, so I guess I'm kind of brushing under the rug the issue of how you're generating the randomness. So we are in the model where you have access to a random number generator, which is assumed to be secure.
Kunal?
Yeah.
So if I'm the database, do I have to remember what I drew from the Laplace distribution if I'm asked again?
Okay, good question. So naively, no, you don't have to remember. If you're asked the same question, I could again add fresh randomness and give a new answer. Doing that will cost me in privacy. So if I am actually able to remember answers to previous questions, that does allow me to kind of get a better privacy utility trade-off. And that's kind of a much more general statement. If you have, if you're asking, say, many queries like this, being able to correlate the answers to these questions allows me to actually get much less noise than you would think otherwise. Yeah, so this was, I guess, somewhat surprising at first, starting with the work by Avram, Blum, Liggett, and Roth. But in fact, now we sort of know that there is sort of a big gap.
If instead of the definition you had e to the epsilon, just said this, the more what I think is the more standard 1 plus epsilon. What did you just end up saying? Just shift all the values by epsilon?
So having e to the epsilon.
Magical mathematics that I think is created here that actually is just an artifact of the definition.
Yes. Well, yes and no. So having an epsilon in the exponent allows me to add epsilons. If I had 1 plus epsilons, I would have to do a more complex.
Multiply them. When epsilon is small, when you multiply them, they add additively again.
Yes. So I guess the composition theorem becomes more ugly and actually harder to reason about. Good. So note that this distribution actually has expected value which is quite small, something like 1 over epsilon. If you have n people in the database, just your sampling noise would be square root n. So this is quite small. You can get differential privacy without losing much in utility.
But epsilon is actually going to be a very small number.
So epsilon is 0.1.
If you want e to epsilon to be close to 1, right? Then you have to use very small epsilon. And therefore 1 over epsilon is not such a small number.
So we think of, say, epsilon as 0.1. So 1 over epsilon is 10. If you have a 10,000 people database, a noise of 10 in the answer is not a lot.
How much is e to the 0.01?
Probably 1.011.
Somebody with Google can tell us the answer immediately.
E to the x is 1 plus x when x is small, so it's 1.01.
The second order term is like x squared over 2. So for 0.1, it's pretty small, right? And I mean, I guess, so I think there's a longer discussion to be had on what's a good value of epsilon. I personally think an epsilon of 1 is not a bad value. If I'm not in the database, the chance of something bad happening to me is, I would say, 0 or pretty close to 0. If that doubles or gets increased by a factor of 10, that's probably not such a bad thing. Yeah.
Just to address this question. So this is additive noise happening on a sum, right? So if
Yes.
you had 10 people, they were randomly sampled, you'd expect kind of square root of n random kind of anyway. So
Yes.
this could be low order of that if epsilon is less
Exactly.
than 1 over root n.
Good. Skip over another building block. So let me say a little bit about composition. So what I described was basic composition, which says that if you run T mechanisms in sequence, each of which is epsilon delta differentially private, it's very easy to show that the sequence is something like epsilon T delta T differentially private. There's actually a stronger composition theorem which sort of replaces this T by a square root T. This term is negligible usually. This delta goes up by a factor of T, but delta is usually much smaller. In some sense, you don't actually pay epsilon times T, you only pay epsilon times root T. There's a better composition that does happen. And in fact, using kind of moment generating functions, you can actually sometimes improve on that as well. So for many distributions of choice, so I guess I'll not get into this, but you can define a privacy loss random variable which is uniformly bounded for pure differential privacy and bounded with high probability for epsilon delta differential privacy. For many mechanisms, you can actually control the log of the moment generating function of this random variable. The log of the MGF itself composes, which is actually very nice. So you can do all your composition in this moment generating function domain, and then you can translate to epsilon delta using Markov's inequality. You can do a lot more. Once you have these building blocks, you can put them together to do lots of more interesting things. People have built recommendation systems such as the Netflix challenge. You can build decision trees. You can do principal component analysis. You can generate data that looks like real data. You can even do some neural network training while guaranteeing differential privacy. Here are some pictures that I will not get into. There's also a large number of connections that differential privacy has to many other fields. So I think it's a very rich and interesting area of research. And I guess with that, I will basically just summarize. So just to reiterate, I think there's plenty of evidence in the form of privacy attacks that just ad hoc approaches to making data private is just broken. Differential privacy is a strong principled way of getting around this issue. And you can actually do a large number of fairly interesting, non-trivial data analysis tasks while guaranteeing differential privacy. I'll stop here. Thanks.
Welcome, Marika prepared. We can take some questions. We need 2 minutes, yeah?
Yeah.
Just heuristically, can you tell me a little bit about the impact on accuracy for some of these machine learning tasks? Like, what do the constants look like?
So it depends a lot on the size of your data set. So for, I guess for modern large data sets, it's pretty small. So I guess one example, okay, so I guess I'll just show you. Oh, okay, well, then I'll just say. So say, for example, for the MNIST data set, where kind of the simple neural network that we train gets something like 98.3% accuracy. We can get 95 with epsilon equals 2. And this is a relatively small data set, it's only 50,000 training images. We would expect that when you have larger data sets, your overhead would be smaller. But that's kind of a question that will need some more empirical work. I think often when you have larger data sets,
Clinical trial where n might be a couple hundred.
That's a very difficult situation. So for a few hundred, I think most of our techniques actually would incur a non-trivial loss in accuracy because, yeah. I mean, if you exactly knew one question that you wanted to ask, we can probably answer it very quickly. Typical data analysis, you want to run a sequence of queries, and then your even the better composition theorems actually add up.
Thank you.
Okay, thank you.